All right, today we'll be working on the linear approximation. So let's try to understand the meaning of this linear approximation. For example, we have a function like the one shown here in red. Suppose that function is y equal to f of x. And if you want to find the equation of the line tangent to this function at, let's say, this point on the curve, somewhere over here, suppose that point is at x equal to a, and you can call that point as a comma f of a. So when you try to find the equation at this point at a comma f of a, what we need is we need the point, we have the point, and we need the slope. Slope of this line will be the derivative at this point, that will be f prime a. So if you want to find the equation of this tangent line, it will be, if you remember the formula, it is y minus y1, the value of y1 is f of a, is equal to the slope at this point is the derivative at a, so it will be f prime a multiplied to x minus a. So y minus y1 equal to m times x minus x1, because the coordinate over here is a comma f of a. Now if you want to find the value of y from here, this is equal to f prime a x minus a, and if I move this f of a to the other side, it will be plus f of a. Now this line, this equation is the equation of the tangent line here. This is the equation of the tangent line. And this function is a linear function. So the tangent line, the straight line, is a linear function. Now, if you try to analyze the tangent line and this function together, you can see that for the points around a, for the points around x equal to a, you can see that if I go down here all the way up to somewhere here, if I go from here on this side towards the left, all the way up to here, you can see that the tangent line and the graph are together. They are one above the other. On the other side, maybe from here up to here, you can see that the tangent line and the function are together. After that, you can see that the value of the linear function is more than the value of the function. And on the other side, the value of the linear function is less than the value of the function. So around this point, around x equal to a, the value of the function, you can see from this point here, maybe from here, somewhere up to here. In this range, the value of the function and value of the tangent, they are the same. So over here, the value of the function and value of this linear function or the tangent line, they are the same. That means if I want to evaluate the value of this function, if I want to find the value of the function around x equal to a, I can either plug into the given function, or I can also plug in to this linear function or this tangent line to approximate the value. By plugging into this value or to the tangent line, the value may or may not be equal, but it will be approximately equal. And we call that a linear approximation. We are approximating using this linear function. So instead of calling it y, we also call it L of x, the linear function. So that linear function L of x is equal to f prime a, the same equation, f prime a times x minus a plus f of a. So that function there approximates the value of the function around x equal to a. So this equation L of x equal to f prime a times x minus a plus f of a is the function or the equation to approximate the value of the function using linear approximation. Now let's try to analyze something here. You can see here, if you look at this equation, the starting point, that is same as the equation of this linear function or the tangent line, y minus f of a equal to f prime a x minus a. What we are doing is we can represent that y with f of x. So if I replace that y by f of x, it will be f of x minus f of a, which I have written here. F of x minus f of a is equal to f prime a x minus a. Now, if you look at the left-hand side, I use the approximation sign because I'm using the linear approximation. That's why in place of equal to, I'm using approximate sign. So if you look at the left-hand side, this is the difference between the value of the function and the actual value over there. So that is the change in the y value. So f of x minus f of a, that is change in the y value. We write that as delta y, or change in y is approximately equal to the derivative of the function at a multiplied to x minus a. X is the value on the x-axis. A is also the value on the x-axis. So that is difference in x value. So delta y is approximately equal to f prime a delta x, where delta x and delta y are small change in x and y. That means we can use this formula to find any change in y when the change in x is given, or when the change in x is given, this is the formula to find change in y, or when change in y is given, this is the formula to find change in x. So that is another important formula that you need to remember from this slide. Change in y is equal to change in x multiplied with the derivative of the function at a. Example, find the linear approximation, that is we have to find L of x for this function, which is f of x equal to cube root of x at x equal to 2. And then we have to use that linear approximation that is created here to approximate the value of the function at 2.03. So let's first find the linearization of this function. So what we know is we have the formula L of x, the linear approximation is equal to f prime a x minus a, f prime a multiplied to x minus a plus f of a. That is my formula. So they have given the function. Let's find the function and the derivative. So our function, it is already given. Our function is f of x equal to cube root of x. Cube root is x raised to 1/3. So we can write that as x raised to 1/3. That is your function. And the derivative will be, and the derivative is f prime x is equal to, if you want to find the derivative of this function, what you'll do is you'll bring this power in front because we'll be using the power rule. So it will be 1/3. And then you'll reduce the power by 1. 1/3 minus 1 is negative 2/3. Negative 2/3, we can write 1 over 2/3. So that is the derivative of the function. Our function is f of x equal to x raised to 1/3, and derivative is 1/3 times 1 over x raised to 2/3. Now what we have to do is we have to find the, if you look at this formula here, we have to find the derivative at a and the value of the function at a. That is, we are going to plug in 2 into these two functions. So the first one will be f of 2, that will be equal to cube root of 2, or 2 raised to 1/3, which is cube root of 2. And if you try to find the cube root of 2, it should be 1.26. That is 1.26. And then if you want to find the derivative at 2, it will be 1 over 3 multiplied to 1 over 2 raised to 2/3. If you try to simplify that, it should be 0.21. 0.21. So now we have the value of the function at 2 and value of the derivative at 2. So our formula for the linearization is, we have the formula L of x equal to this formula here, f prime a. So in this case, it is f prime 2 x minus a, that is x minus 2 plus f of 2. So let's plug in the value. The linear approximation is given by, okay, the derivative is derivative at 2 is 0.21, 0.21, then you have x minus 2, plus the value of the function at 2 is 1.26. 1.26. So the linear approximation L of x is equal to, if I multiply here, 0.21 multiplied to x is 0.21x, then minus 0.21 multiplied to 2 is 0.42 plus 1.26. So this implies the linear approximation is equal to 0.21x, and then here we have 1.26 minus 0.42, which is 0.84. So that is the linear approximation of this function at x equal to 2. So you can box that answer. Now we need to find the approximation. So we are going to find the value of this function f of 2.03, f of 2.03. This value will be approximately equal to L of 2.03. So instead of plugging into this function, you can plug into this one. You should get approximately the same value. Let's see what we get if we plug in L of 2.03. That is, we are going to plug in 2.03 in this function. So it will be 0.21 multiplied to 2.03 plus 0.84. Now if we simplify this using calculator, what I got here is 1.27. Example, find the linear approximation to the function f of x equal to the natural log of 1 plus x at x equal to 0. Use the linear approximation to find the natural log of 0.9. So we know the linear function. So what we have is L of x, the linear approximation, is equal to f prime a x minus a plus f of a. So in order to find the linear approximation, we need the value of the function at a and the derivative of the function at a. So first we are going to find the derivative of the function. So here my function is natural log of 1 plus x, and its derivative will be, using the chain rule, it will be 1 over 1 plus x. So the value of the function at 0, because x equal to 0, that's the value of a. So if you plug in 0, it will be natural log of 1 plus 0, that will be natural log of 1, and natural log of 1 is 0. And the derivative at 0 is equal to 1 over 1 plus 0, that is equal to 1. So the linear approximation will be, now the linear approximation L of x is equal to f prime a, so f prime 0 in this case, when we plug in 0 for a, f prime a, that is f prime 0, x minus 0 plus f of 0, which is equal to, the linear approximation is equal to f prime 0 is 1. So that is 1 times x minus 0 plus f of 0 is 0. So we get the linear approximation as x. So L of x is equal to x. Okay. Now to find the approximate value, we are asked to find the natural log of 0.9. Natural log of 0.9. But our function is given in the form 1 plus x. So that is equal to natural log of 1 minus 0.1. Because 1 minus 0.1 is 0.9. So by doing this, it looks in this form, in the form of the function given here. And in place of x, I have negative 0.1. And in order to approximate this, we are using the linearization function L of x. and x is negative 0.1. And what we know for our linear function is L of x is equal to x. So whatever is the input, the output is also the same. So the value will be equal to negative 0.1. So the approximate value of natural log of 0.9 is negative 0.1. Example, the atmospheric pressure at altitude z is given by the function pressure at altitude z, that is Pz, is equal to 1000 multiplied to e raised to negative z over 10. We have to approximate the change in atmospheric pressure. Meaning of that is you have to find the change in P, that is delta P, when the altitude increases from z equal to 3 kilometers to z equal to 3.01 kilometers. So what we know is, to find the change, we have this formula. Let me write here because it is in terms of P and Z. So what we know is change in atmospheric pressure delta P is equal to derivative of the pressure at 3 multiplied to del Z. So that is the formula that we'll be using here. So here Z changes from 3 up to 3.01. So by looking at these values, you can tell that change in Z is equal to 3.01 minus 3, that is equal to 0.01 kilometer. So altitude increases by 0.01 kilometers. So as the altitude increases, let's see what happened to the atmospheric pressure. So we have the value of Z. Now what we need is, we have the value of change in Z or change in altitude, and we need the derivative of the pressure at 3. So here we have the pressure formula for the pressure. So let's write down here the pressure at any altitude. Z is equal to 1000 multiplied to e raised to negative z over 10. So if you want to find the derivative, then it will be P prime Z, the derivative of the pressure function, is equal to 1000 is a constant multiplier, so it is multiplying with that function, so it will stay right there. 1000 multiplied to e raised to negative z over 10. So this is the composite function. Your outside function is e and inside function is negative z over 10. So the derivative of the outside function first, e raised to anything is e raised to that. So e raised to negative z over 10 multiplied by the derivative of inside function. Derivative of negative z over 10 is negative 1 over 10. Negative 1 over 10. So what I'm getting is the derivative of the pressure is equal to 100 multiplied to negative 1 over 10. 1000 multiplied to negative 1 over 10 is negative 100. Negative 100 multiplied to e raised to negative z over 10. So that is the derivative of the pressure function. Now we are looking for the derivative of the pressure at 3. So we are going to plug in 3 into that function. So let's plug in the value of z as 3. So change in pressure at 3 is equal to negative 100 multiplied to e raised to negative 3 over 10. So the derivative of the pressure at 3 is equal to, if we simplify this using calculator, negative 100 multiplied to e raised to negative 3 over 10 is negative 74.08. That is the change in pressure or derivative of the pressure at 3. Now we need to find the change in pressure, which is delta P is equal to this formula here, which is the derivative at 3 multiplied to change in altitude. So that is equal to the derivative of the function at 3 is negative 74.08. Negative 74.08, and we have to multiply that with the change in altitude. Change in altitude is 0.01. So that is equal to, so if I multiply these two, negative 74.08 times 0.01, that is equal to 0.74, but negative 0.7408. So that is the change in pressure. I don't have the unit of pressure given in the problem, so I'm just going to write units, whatever the unit of pressure may be. So that much unit per kilometers. So that is the change in pressure with altitude. And you can see that as the altitude increases, when you're going away from the surface of the earth, the atmospheric pressure decreases. Differential, suppose you have a function y equal to f of x that is differentiable on the interval containing x, or that is differentiable around the point x. For a small change in x, and that small change in x is denoted by delta x, and we also read this as dx for the differential. The corresponding change in y is also known as the differential y, which is written as dy, is connected by this formula. That is, differential y is equal to the derivative of the function at x multiplied with differential x. So this concept will be very important in the integration of the function using u substitution. So computation of the differential will be found useful while computing the integrals using u substitution. That's what we are going to explore in next week. So here we are talking about the differential. Whenever we are asked to find the differential y, that is equal to the derivative of the function at x multiplied with the derivative of x. So I mean the differential x. So let's take an example and see how we can use that. So here we have the example. Example, use the notation of differentials to find the approximate change in the function y equal to f of x. Change in the function value means we are looking for dy when there is a small change in x, that is dx given to you. So let's see how easy is this one. This must be very, very easy. You'll love it. So in part A, you have f of x equal to 4 sine squared x, which can be written as y equal to 4 sine squared x is sine x times sine x. So I'm going to write like that. Now let's find the derivative. If you want to find the derivative of y with respect to x, we write dy over dx. dy over dx is equal to, now if you want to find the derivative of this one, 4 is a constant multiplier. It will stand right there in front. Now, in order to find the derivative of sine x quantity squared, you can see you have an inside function of sine x and outside function is a power function. So we have to use the chain rule here. Chain rule says derivative of outside function, that is the power function. For that, we bring the power in front and decrease the power by 1. So when you decrease the power of sine x by 1, it will just be sine x. And then we have to multiply by the derivative of inside function. Derivative of sine x is cosine x. So dy over dx is equal to 4. Now 2 sine x times cosine x, if you remember from your trig class, it is sine 2x. 2 times sine x multiplied to cosine x is sine 2x. That is the formula from trigonometry. We are looking for change in y. So this implies differential y, dy is equal to 4 sine 2x. If you multiply on both sides by dx, so that dx will go there. So that is your differential y. Differential y is equal to 4 sine 2x dx. Okay, B. In B we have f of x, that is y, equal to sine inverse 3x. So now the derivative will be dy over dx is equal to, in order to find the derivative, you can see this is the inverse sine function. And also this is the composite function. Your outside function is sine inverse and inside function is 3x. So for the composite function, we use the chain rule. Chain rule says the derivative of outside function multiply by the derivative of inside function. So the derivative of outside function, derivative of sine inverse x is 1 over the square root of 1 minus x squared. In place of x, I have 3x squared. Then multiply by the derivative of the inside function. So derivative of the inside function. That is equal to dy over dx is equal to, here in the denominator, I have 1 minus 3x quantity squared is 9x squared. And in the numerator, the derivative of 3x is 3. 3 times 1 is 3. So the derivative is 3 over the square root of 1 minus 9x squared. I'm looking for dy, so I have to multiply on both sides by dx to get rid of this. So dy, that is differential y, or a small change in y, is equal to 3 over the square root of 1 minus 9x squared multiplied with the differential x. So that is the value of differential y in this case.